All right, welcome to part 2. So like Lily, I also have a Colab notebook. You could find the right one. Nope. There we go. All right, and I'm also going to give you, this is a copy of, where's the chat? There's the chat. All right, here is I put a few things in here. One is everything I'm going to do sort of expanded out. And then the live tutorial, which I'll be just working through and editing as we go. And if you want to copy it, there's a copy that you can edit or copy on your own. I will. The specific one I'm going to be working on is this. You can sort of watch it update in real time if you like. So, right, the dependencies for all in this one chat. The dependencies for everything can be a little bit complicated, especially in Colab, which is stuck at Python 3.6, I think. So I've already done this, but basically, in order to get matplotlib to be at the right version and everything else to also be at the right version, you sort of have to run a few things and then restart. In fact, here I'll do that. So basically, after you run all these installs, then you have to go to the runtime and restart the runtime with this, which I won't do right now because it should already be done. But I'm going to go ahead and scroll down here just to make sure. All right. So for this, let me hit run. So whenever it finishes loading, we'll see what happens. I'm going to use a really basic model, S1 to S2, S2 to S3, mass action kinetics as the base model, and then I'm going to add a variety of other things into it as we go. So there are, basically, you know about species, you know about reactions. You can actually give a reaction a name if you want, like that. You can use those, and then if you can use those reaction names if you want to like ask what it is, like rr.j0. So the actual value of J0 or of the flux of S1 to S2 at the end is kind of low. It's lower than it started off to be. In fact, here we can do this, right? So it starts off at 3, you run the simulation, and by the end it gets to 0.14. So you can keep track of those sorts of things. But that's not antimony. So assignment rules. Assignment rules are one of a thing you can do to set a value always equal to some formula. So let's see. Look at my notes here. So, right. So let's say that S1 is not changing, and it will not change in time like that, but it actually is like a fixed input that is the sign of time or something. Oops. So let's look at what that does. Oh, it doesn't like it at all. Oh, right. And it doesn't like that because now that I've told Antimony, or I've told SPML and the simulator that S1 is changing in 2 different ways. I've told it that S1 is changing as the sign of time, and also I've told it that it is changing, it is being consumed by this reaction, and it can't do both at once. So it says, hey, I can't do both of those things at once. So a quick way to change that in Antimony is to set S1 as a boundary species. If you set it as a boundary species by using this little $, you can also say X S1. So either of those methods will work. And then that means that that species cannot be changed by reactions anymore. So if we do this, so it doesn't like it. What is it like? Oh, right. And then I can't say that it is equal to 5 when I've already said it's equal to time. So there we go. So now S1 is changing and is an external species. It's varying in time, and when we simulate, we get this. Now you'll notice that by default, S2 and we're only seeing S2 and S3. That's because if you don't tell it to do anything else, it'll say that the selection list is all the floating species, and since S1 is now a boundary species, it doesn't want to do it anymore. So let's change that. Time course selections equals time S1, S2, S3. So put S1 and S2 back in, and here we go. Now you'll notice S1 is actually going negative. Roadrunner doesn't care if things go negative. You have to set up your model in such a way that it won't on purpose. One way we could do that is we could say, let's see here, we'll make this a piecewise function. So we'll say that it's 0 if the sign of time is less than 0. Otherwise, that. Let's hope that actually works. Ooh, look at that, right. So now S1 goes up and down, but instead of going lower, it flatlines at 0. Here, let's do this so we can see. Oops, yeah, times 3. All right. So now we're seeing this it's a sign except over it has a minimum of 0, and so now nothing ever goes negative, which is probably more biologically reasonable. So that's the basic ideas behind different things you can do with assignment rules. You can make this formula as complicated or as simple as you want. You could even say that here, we'll make it S2 plus 3 and see what happens. So now S1 is always equal to 3 more than S1 is always equal to 3 more than S2. It keeps on going up even as it's creating more S2 here. So obviously, like as you go, things will be, you'll keep getting more and more stuff in here. Let's go back to this just equals 5. And another thing you can do is something like S total colon equals S1 plus S1 plus S2, S2 plus S3. And we'll put that on our time course selection lists. This obviously is a different way of you can put that as an argument to simulate, or you can just set it here. Both of those work. Oh yeah. Why is that going up? Oh, because it's fixed. S1 is fixed. If I unfix it, it's still fixed because I said it x'd. And there we go. Okay, so once S1 actually becomes a floating species again, it goes down over time, and the total of everything together stays the same as you would expect. But now this is sort of a validation check, if you will, because you are actually like taking the current values of S1 and S2 and S3 at every time point and plugging them and saying that S total is that value. Any questions about assignment rules, sorts of things you can do with them?
I was just slightly
confused
with the xed. You had xed S1.
Yes.
And I was simultaneously trying to track down the Antimony user guide, but
Oh,
Did you declare it as X because you made it a boundary?
right. So declaring it
Condition?
as X means that in antimony, that means that it is a boundary species. That's how I'd say that it is. So if I say X S1 and rerun it, now S1 is fixed and it will always stay at 5 and won't change from anything else. Another way to do that is to use a $ by it.
Okay, so I think you answered my question.
Okay.
It's either one is sufficient.
Right. Either one is
Okay.
sufficient. Yeah.
Thank you.
Yeah, sure. All right, let's do rate rules. So rate rules are saying how something changes in time. So this time we'll say S1 starts at 5, but then we'll say S1 prime or equals -0.3 or something. And again, if we say this that it is changing at a rate of -0.3 and that it is in a reaction that is changing at a rate of -K1 times S1, that's over determining the model, and it doesn't like that. So we have to do that instead. So there's S1 going down and S2 and S3 going up. And let's do this again. Put that here. Set our time course selection so we can see what's going on and show that. Now here you see that S1, it's going down slowly, but it's not going down as fast as it used to, as fast as S1 is going up. So the total amount of species in this model is actually going up over time. So we're essentially saying that the reaction is not consuming S1. Instead, some other process is slowly taking it out of the system instead. So basically, S2 is being created. This says S2 is being created essentially ex nihilo. If you have nothing but fixed or boundary species on the left side, then that's the same. In fact, if I do that, exactly the same thing will happen. So the only reason to put a $ S1 in there is just sort of to make you remember that that's what the reaction is actually doing under the hood. But when you fix it, you are saying mathematically it is not being affected. The only thing that is being affected is S2. We can also like exactly reproduce what was going on before by just saying I can say this is the rate law for S1, how it changes in time. It's -K1 times S1, which is exactly what it would have been. And so the resulting simulation is exactly the same. If we wanted to do the same thing for S2, we could do that too. But this time S2 is being changed by two things. So it's K1 times S1 in a positive direction minus K2 times S2 negative direction. Again, we have to put in our $signs. Don't think you don't have to put them in everywhere, but and then now this reaction, it's entirely doing nothing because the left side and the right side is both fixed. This reaction is only creating S3, and all of the functionality we've moved into rate laws and say like this is this rate law, this is this other rate law. If you look at a lot of papers, they will often describe your system of ODEs this way and just say, this is the rate of change of S1, this is the rate of change of S2. So if you want to do that quickly in Antimony, you can just do that. It tends to be better as far as the types of analyses you can do to actually convert things into reactions properly. But sometimes there's nothing for it, or sometimes it actually is something is being controlled by a different force entirely other than reactions. You just have to say like, all right, this is how it is changing in time, or this is how I'm going to make an assignment rule for it instead. Any questions about rate rules? Right. Functions. So this is sometimes a little bit less useful for a tiny model like this. You have your mass action kinetics and your in all of 2 reactions, right? So you don't necessarily, like, that's going to be fairly obvious what's going on. But if you have, say, 100 reactions and half of them are mass action and half of them are Michaelis Menten or something, you may want to just define a mass action rule, the math of a mass action rule, the math of Michaelis Menten, and do that separately. So the way we do that is with function mass action AX, and then we have to, at the end of the function will the end keyword, and then you just write the formula here, K times X, which is a really simple thing. But so now instead of like actually putting the math here, we say mass action K comma, and we'll do the same thing for this. And you can imagine having even more. I mean, for obviously something like this, you would just write K1 times S1. But the result is going to be the same. So now you've defined a function elsewhere, and then you can write it here. And then if you want to say, I don't know, say like it's mass action, but there actually is a like a little bleed through of some things, like sometimes things just happen. We can change, then you can change the mass action formula for everyone and everything happens all at once. And you get slightly different because that wasn't large enough to change. See here, we'll do that. All right, fine. We'll go all out and say +1. All right. So now, if we don't have true mass action, but instead have mass action +1, so like some things just happen. Now S1 is actually going negative over time, and we have, and in response, S3 is like going up above 5. So we're trading imaginary S1 for real S3. Obviously, that's less of a real example than just sort of an demonstration of the sort of thing you can do. One thing I will say with functions is that if you import a model from SBML that was created with Coposi will automatically make every rate law into a function. So you end up with a lot of these functions at the beginning of your model. Mostly I'm showing you this just so that when you import a Coposi model into Antimony or something, you see all these functions, like, what is this? That's probably what's going on. It's just defining everything as a mass stack or as some sort of rate law. Sometimes it'll actually be like the J0 rate law, the J1 rate law, and so they won't be used more than once. But sometimes they get a little bit of reuse out of them. All right. That is the basic functionality of functions. Any other questions about that? Thanks for jumping in with questions, by the way. It's useful. All right, compartments. Now, so far, I haven't talked about compartments. That means that by default, Antimony will put everything, all of its species, into what it calls a default compartment. So if you want to define multiple compartments, you say, the fastest way is to say in C1, S2 in C1, and S3 in C2, say. So now I've placed my species S1 in compartment 1, species S2 is also in compartment 1, but now S3 is in compartment 2. So that doesn't change anything about the reaction right now, right? It's just the compartments have a default value. So C1 equals, and then a default value of 1, C2 equals 1. So, and I've just explicitly said what those are. And again, nothing is changing. But now let's say C2 is actually much larger than C1. So we have all these reactions going on, and they're pumping out S3 into a new compartment with a different volume. So what would you guess would happen to this graph with S3? Anyone? We're plotting the concentration of S3 here. Won't keep you in suspense much longer, but so the deal is that everything, all reactions under the hood, we talk about things in terms of concentrations a lot, but under the hood, everything is happening in terms of amounts. So if you have a certain amount of S2 turning into S3, it'll be turning into an equivalent amount of S3. And then it'll place that S3 in a particular volume. And so if that volume is larger, it'll look smaller, even though the amount is actually the same. So we would expect to see exactly the same thing here, but the green line will be much lower. And that's indeed what happens. Now, if instead, let's see here. Where was I? All right. So if I asked for my time course selections this way, because I don't have the asymptote anymore, you'll notice here that this is S1 and S2 and S3 in square brackets. That means concentration, and by default, that's what it treats everything as. But if I tell it just plain S1 and plain S2 and plain S3, then that treats it as amounts. And if I do that, the amounts are exactly the same as they used to be, even though the concentrations have changed. So yeah, so the total amount of everything is the same. But if the compartments were different sizes, then that can change like that. Let's comment that out again. Compartments also can change with rate laws or anything else. So let's say that equals -1 or something. So let's say that C2 is draining, and when you change the volume, you are just changing. You aren't like, if you take away half of the volume of something, you leave all of the species that were in it sort of magically go into the part that you didn't take away. So when you drain something mathematically like this, you are just saying that it is the water basically that is increasing or decreasing. So now, wrong. So now since C2 is changing in time, by default, it's showing you what it is over here. And however, let's take it back off so we can see it more easily. So now this green line sort of looks like almost like a cross between what it looked like in sort of a standard. So in the standard model, it was going up to here. It would eventually reach 5. When we took it down, said that it was going into a compartment of volume 10, it went way down to that. So now it's sort of halfway between. Let's say the C2 equals 4. I don't want to get to 0, but nope, it did. So we actually have like a negative concentration thing here, which is not very helpful. Yeah. There. So now we see S3 like as the volume of the compartment into which it's going is shrinking, its concentration is shooting up much faster than it otherwise would have. So again, these are sort of made up examples, but you can certainly imagine that even just having fixed compartment sizes can be useful. If you have something pumping stuff from the mitochondria to the nucleus or from the mitochondria to the cell main compartment, or from a cell to the external concentration, to the external extracellular matrix. The sizes of all those compartments are going to be very different, and reactions happen at the level of the actual molecules. So you want to keep track of that, and SBML does that for you, and the Roadrunner does that for you under the hood, and as does Antimony here. So that's a quick overview of compartments.
Lucian, I had a question. How would you typically show a species moving between compartments? Like, say something is phosphorylated and then it moves from, moves into the nucleus. What's the
right? So in SBML, every species, what it calls a species, is actually a particular molecule in a particular compartment. So if you have ATP in both your nucleus and in your cytoplasm, then you have ATP cytoplasm and you have ATP nucleus, and those are two things. And if you have transport, then you would say ATP cyto goes to ATP nuke at a certain transportation rate, trans times ATP cyto or something. Or maybe it's just, or maybe at the level at which you are working with, there's just a transport reaction that doesn't really care how much there is, and now it will just pump everything from the cytoplasm into the nucleus. You do have to be careful for these sorts of things that you don't go negative. You can certainly, it's easy to write models that are non-biological in nature, but it's also fine to write math that would be non-biological in nature outside of the range of your experiment, but in your experiment it all works out, so it's fine. Does that answer your question?
Yeah, that's great. Thank you.
Okay. I think there's one other thing, isn't there, that when you write the rate law for transport, it should be the unit should be amount per unit time. Yes.
Yeah. In general, all these K1s and whatever these things are, they will always be amount per unit time, not concentration.
Yeah, but you have to multiply by the volume, don't you? Or does it automatically multiply by the volume? Oh, it automatically does that, doesn't it? Internally.
Internally,
you don't have to do anything.
Everything is,
yeah, you don't have to do anything, actually. It does it automatically. Yeah.
I think so, yeah.
Yeah.
It will move things in terms of amounts. You can, there actually is, let me see here.
So what happens is, so the rate is in terms of concentrations, right? Like if it's K trans times ATP cytoplasm, ATP cytoplasm is the concentration in the cytoplasm. But under the hood, what it does is then converts that rate then will be concentration per unit time. So what it does under the hood is it takes the volume of the cytoplasm. So ATP, he hasn't said where ATP is in, but if you had you got C1 and C2.
Sure.
If maybe you want to put ATP in
C1.
If you called it C1, for example, I mean, you can use any name you want here. But C1 has a volume of 1, right? But C2 has a volume of 10. What it'll do under the hood is multiply the concentration per rate into amount per rate to account for the differences in volumes. So if you're moving, for example, let's see, from a high volume to a low volume, you'll see the concentration in the low volume compartment rise faster than the concentration dropping in the big compartment. So from your point of view, you don't have to really do much. All you have to do is say where each of these which compartments each of these species are in. That's all you really have to do. And it'll take care of the rest.
Yeah.
I don't know if that made sense or not.
Yeah.
Basically, on your side, you don't have to do anything. Just say what compartments they're all in.
If you tell them what compartments they're in, if you set the volumes, everything should work. Yeah,
everything should work. Yeah.
I will make this a little bit less.
It feels too easy.
Awkward. It's like, really? That's it? So
yeah, well, it took a
here's
long time to get to this point.
here's the ATP in the cytoplasm going to the ATP in the nucleus. The cytoplasm is a much higher volume, and so therefore, once it goes to the nucleus, it's going to have a much higher concentration once it gets there, right? If we're pushing it in terms of its concentration, and the concentration starts off really high, it's going to zoom up even though the volume is high. And indeed, so here's the red ATP cytoplasm is slowly going down. ATP nucleus is shooting way up.
Yeah,
because
because you're moving mass into a very small volume.
Right.
So the concentration will increase much faster.
Yeah. That was a good question.
Mm-hmm.
Anything else?
Now, by the way, if your volumes are the same, you don't have to worry about this.
Right.
You don't have to think about it. But if they're different, then you do.
Yeah. 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 If they're different, or if they change, or if you, I mean, if you just sort of want it to be accurate. If the other thing that to consider sometimes when you're building a model is that you're building a small model that someone may want to come along and expand later. So if you tell it, if you have all the information about which compartments it's in, what the actual species it is, you're making their job a lot easier instead of just saying the default compartment or something.
Mm.
All right, distributions. Let's say, so Lily told you earlier about Gillespie simulations, and simulate is completely deterministic. However, you can actually in your model put in some stochasticity and make it draw from a distribution. So instead of saying S1 equals 5, let's say S1 comes from a uniform from 4 to 6. So S1 is anywhere uniformly distributed between 4 and 6. So we run it, and it started about 5 anyway. So let's make sure that print there's one here, and we'll say at the beginning. There. So that run through was 4.29. Another one, 5.76. Oops. Did I go to the next one? I went to the next one. 4.05, etc. So you can actually, in the actual model itself, you can say, I don't know exactly what this value will start at. So let's do something a little bit more complicated. And we'll just repeat this simulation a few times for in range 100. And we don't want to forget, reset it. And then, will this work? I'll pick this up from Lily's thing.
I can never remember.
Stop. Stop. All right.
You might want to do a few less than 100 to begin with.
Yeah. Plot array. I think, is that it?
No.
Nope, that's not it.
Just try TE plot.
TE plot?
Maybe. Yeah, I always forget this bit.
Okay, never mind. Here. What I remember is how to do this in Matplotlib. Okay.
I think plot array will work, but you have to plug in the result as an argument.
Ah, okay.
That's true, yeah.
Plot array results.
Get rid of your input.
Oh, because I was in the middle of importing something. All right. Nope. Oh, stop. I probably shouldn't do this.
Oh, you have to do the show equals false for the plot array.
Got it.
Yeah, that's it.
Capital F.
All right. Haha, look at that.
There you go.
Very nice. All right, there's our nice little blended plot of a S1 starting at a uniformly distributed between 4 and 6, and then all the different plots that came out of that, the different times we ran it. You could also let's say we don't want to change S1, but we want to change actually S1, K1. So, and then instead of a uniform, we'll use a normal. Say the mean is at 0.6 and give it a range of standard deviation of 0.2.
Could have some weird effects here if K1 goes negative.
Yeah.
But anyway,
we have to set this to all lonk. There we go.
I know you
So now
got away with it.
I got away with it. Yeah. So now S1 started at 5 and it went down at a variety of different rates. And if we collect this, all k's equals this, and let's say all k's and k1 print all k's. Then we have to import matplotlib here. No, or number. It's not going to work.
Yeah.
Whew, look at that.
609.
So yeah.
Sort of a poor man's parameter scan.
Yeah. Yeah. So we set k to a wide variety of values, but the mean was indeed 0.6, just like we told it to be. It was close to 0.6 because obviously it was only 100 draws, so it won't be exact. As you were implying, if we if we have something like this, so a lot of times we're going to have negative k's. It goes up and down like that. So one thing we can do is say we want it to have a minimum of 0 and a maximum of infinity. And now when we run it there, by having a few more arguments to the normal function, we can give it bounds. So normally it would have negative values for k all the time, but in this case we set a lower bounds at 0, and then it won't go any smaller than that. So we had things that are pretty close to 0. This 5 is here. We'll say print. Oops. Be the min all k's. Try that. Yeah, so the minimum of 0.005 is what happened to choose. All right, nice. Yeah, so there are other distribution functions besides uniform and normal. Uniform and normal, between the two of them, you can use them for anything else. But yeah, there's like the Poisson. The most useful ones are probably things where you want an actual integer. So there's a few distributions that will always give you an integer value or something like that. But there's, I think, like a dozen or so different functions that are in SBML, and then we're also in Antimony. So again, all of this will in theory be portable to other programs if they support distributions, and if they don't, then you can write them and say like, hey, you should support distributions, and in the meantime you can just use your Roadrunner because your Roadrunner supports distributions. All right, any questions about that? Events. So an event is something you can do this in a variety of ways, but if you actually want to bake it into your model, there is ways in SBML and Antimony to encode something that happens. So let's say S1 starts at 5, but at time is greater than 2, S1 goes back to 5 again. So we're imagining that like we let the experiment run for two seconds, and then we pause things and like inject more S2 until we get up to our original concentration and continue. So that's exactly what we see. And in fact, here we'll say something just to the point at which it printed it wasn't quite. The only reason why it looked lower was because of the resolution of the graph. So if we print enough points, it will actually show it going up there. So now we've, like, time has passed, we can set things, and we can set a few things also. We can say S1 equals 5 and S2 equals, I don't know, we'll reset everything back to the initial conditions, basically. So now we go on for a little bit, reset everything to initial conditions, and then keep on going, except for S3. S3 continued to where it was, and it kept on going up. If we were to see, let's see here. S0 equals S1 plus S2 plus S3 colon equals. And time S1, S2, S3, S0. Nope, didn't like it. Works. No, I don't have enough. Oh, I forgot my bracket. There we go. So now you can see when we did our little event, we basically added a volume of 1 mass. That's because, or I guess not exactly. Basically, we added however much S3 was at that point to our totally reaction. I'm going to copy this and paste it in as a new one. All right. So let's say instead of time, we want to actually have it internally modified. So like cell cycles will often, like, something will trigger and something will happen based on the actual concentrations of things in the cell itself. So instead of at time equals 2, we'll say that at S1 is less than 2, and we'll do the same thing. Sure, why not everything, right? So now every time S1 goes below 2, then S1 and S2 are reset to 5 and 0. And then the same thing happens again and again. Because every time the event fires, it happens again. So the trick is that an event will fire every time that changes from being false to being true. And when at that one time, it will fire once and then be done. Because you'll notice, I'm like, in this case, we said S1 equals 5, but let's imagine we just set S2 to 0 or something, right? So now S1 is just going down smoothly. Suddenly we kill all of S2 and then let the reaction proceed. So in this case, our total volume of protein goes way down because we just pulled out a bunch of S2 out of the system. But the entire last 2/3 of the simulation, S1 was still less than 2, but nothing ever happened because it continued being false and it didn't transition from being true to being false. So that's the trick with events. They have to transition from being true to being false. If I was to say that S1 is less than 10, right? We'll set this to 3 or something. You'll notice nothing happens at all. That's because at the beginning of the simulation, it was already false. This was already false. So nothing changed to change it from being true to being false. If you would like to set up an event to fire at the beginning of your simulation, even if it is true, then you say this. You say at time 0, this trigger is considered to be false, regardless of any calculation. So now, if I evaluate this at t0 and it's true, then I say, like, all right, I have, through the miracle of math, transition from false to true, and we'll do this thing. So now, since we set S2 to 3 at the very beginning of the simulation, that's what it is. S2 was 0, but this event fired before anything happened, before any reaction happened or anything, and set it to 3. And you'll notice our total volume of everything is up here at 8, because S1 was 5, we set S2 to 3, and so the total was 8. Any questions about any of that? All right, I'm gonna do another thing here. All right. So let's say this one's less than 2 again. And then we'll set S1 to 5. So this is basically, okay, so this is our new thing. We're just adding S1 every so often. Now let's do something else. Let's have 2 events that do the same thing, except that they will have different effects. And I'm going to take out S total for now. All right. So we have 2 events, and let's simulate the 15 just to see if whatever time. Oh, hey, look at that. All right. So sort of randomly, and I'm not sure why, but non-deterministically, usually every time that event fired, it set S1 to 7, except for once when it didn't. Is that going to happen every time? Oh no, look at that. It's completely random.
You don't have enough points, maybe.
Oops.
Not sampling enough points.
It's possible, but I don't think so. Oops. I think it actually is like doing it stochastically.
That's odd.
But I think that is just a Roadrunner thing. So in SBML, if you have the situation, it does not tell you what to do. It says like you can fire one, or you can fire the other, or you can fire both. Often what will happen in some simulators, it'll just fire one and then it'll fire the other. In that case, if it was doing them in order, it would always set S1 to 7 and you would never get anything else. So what we want is an actual stochastic. So we set the priority of each one. Priority equals 5. Priority, oh geez, I can't spell priority. Equals 7, right? Well, no, what didn't I like? Oh, I spelled priority wrong. There we go. All right. So now what you'll see happens is that every time it gets reset to 5. So what's going on under the hood in this case is that it executes the events in a particular order. In the highest priority gets executed first. So in this case, the priority 7 event triggers first. It sets S1 to 7. Then the lower priority goes and sets S1 to 5, overriding the previous thing. And the result is that S1 equals 5. So in this case, both of them actually still fired, but only one of them essentially, since they were always in the same order, we always get the same results in the end. You'll also notice, so this event fired first, set S1 to 7, and now S1 is no longer less than 2. But because this event already triggered, it's still going to fire. So first things that happen is everything that's triggered gets put on sort of an event queue, an event stack, and then all of them fire. But you can change that if you like. Oh, no, I'm blanking on what we should do. All right. Ready? Persistent, that's it. Okay. We can say this. So now persistent means that in the time between when it triggers and when it fires, if the trigger condition, S1 is less than 2, changes back to true. Remember, it has to change, or if it changes back to false, it will fire, it will be put on the queue if it changes from false to true. And then if we say persistent equals false, that means that if it changes back to false again before we get to do anything, it won't fire. So remember what happened before was that everything, the 5 took precedence. Now the 7 takes precedence, and it goes to 7 every time. That's because it was priority 7, it set it to 7, and then in setting it to 7, it also turned off the other event because it was set persistent false. So it never gets overridden by the other event. That's kind of a lot to take in. Does that make sense? So there are tricks you can do here also. Let's do this. So now we're going to combine what we were doing before and say the priority is a draw from a uniform. So if we set these both equal to a draw from a uniform, so one of them should always beat out the other, but it should be random. And now you'll see it is indeed switching between the two of them. Let's change this to 25 to sort of get a better sense of how often these things are firing. Yeah, that's sort of happens. Sure looks like it's doing the 5s a lot more. There we go. It should be roughly even, but of course any given stochastic run will be kind of random. There we go. Now we're sort of back in a reasonable set. So if you wanted both of them to fire, to sort of compete with each other at an even level, you can do something like that. Let's say you want one to fire more often. One way you could do that is to do this. So now we set it to 5 and give it that a priority of 0 to 1, but we set it to 7 with a priority of 0 to 2. That means that half the time this draw will be over 1 and it will just fire, and it doesn't matter what the other one did. And the other half of the time it'll be in that same range. So the overall ratio should be 3 to 1, or so 25% of the time it should set it to 5, and 25% of the time it should set it to 7. And I don't know if we'll be able to see that with these small numbers, but in general, you see it setting to 7 a lot more here. We'll run it a few times. Yeah. So this one is now has a higher priority more often than the other one. All right, I think that's about all I wanted to talk about events. Anything else? Uniforms. Delays, that's right. All right, I'm going to go back to a simpler event. So we'll copy this and paste it here, sure. All right. So now, if you remember what happened here, right? Okay. Yes. So at time, just at time greater than 2, we reset S1. Oh, that's not here. We'll do S1 less than 2 because that's more interesting. Okay. So now every time S1 goes less than 2, we set S1 to 5. What we can do with events also is have them trigger at one point, but fire at another point. So triggering is when this part changes from false to true, but firing is when these assignments get made. So we can add a delay and say that 1.2 after S2 goes to 1, then we'll do that. So you'll notice that it first fired around 1.5 here. Now it's waiting until about 2.5 before it finally fires. We'll change this to 10 so we can see it happening a few times. There we go. So now over the course of 0.6 or something, we can see it happen more frequently. Now we've added a delay, and delays are also probably your most likely candidate for the persistent case. So say that so that you have like neuronal firing or something reaches some threshold and triggers some say that you have to have in order for a neuron to fire, something has to be above 5 for a total of 2 seconds or something. What you could do with that, you can say like, I'm just going to do another one. At 2 after S3 is greater than 3, we'll set S1 to 100 or something. But we'll make this persistent. No, we don't have something that goes up and down. Ah, we do have S2. Okay, we'll do S2 here. Okay, I'm going to take this out. And just to sort of look at what's going on for a bit. All right, so we'll see S2 was greater than 2 for a little bit of time. So we'll do S2 is greater than 2. Persistent equals true. We'll set S1 to 100. So let's see if that's enough. It was. So at 2 after S2 was greater than 2, it was still true. It was still true after 2 seconds, so it fired and it made S1 go to 100. Here, we'll make it 10 to make it a little bit more obvious what's going on. So let's say at 4 after that, that's probably too long, right? Nope, it wasn't. At 6, that doesn't make any sense. Huh. All right, that looks like a bug. I should have checked this early. But in general, S2 was higher than 2 for a while, and then it went back down. And because it was set persistent equals true, it should not have fired, because this trigger was no longer true. So you should be able to do that. It's something went wrong. We'll fix that. And moving on. Are there any questions about any of that? Yeah, okay. Let's see. All right, so modularity. I'm going to do a really simple example of modularity here, but you can imagine, and hopefully you can sort of imagine what it would be to be a little bit more complicated. So under the hood, this is a single model, and Antimony gives it a default name and stuff, but you can also just say model reactions. And then at the end, you say end. And exactly the same thing will happen, but if you were to get it, all right, let's, do that. All right, so here's the SVMO under the hood. And you'll see that it has the ID to reactions. Great. How does that help? That helps because if you have more than one models, you can say a model, one reaction, a K, and an X and a Y. And we'll say X goes to Y at a value of K times X. And now we're going to delete these reactions and instead import them as submodules. So K1, S1, S2. B1 reaction, A1, S2, S3. And if I run this, I should get what I had before. But now I've done it sort of modularly. Now what I've done is I've created this very, very basic submodel that is just a reaction. And oops, here, this is actually K2. So that wasn't quite the same because the K2 was off. Actually, that's interesting. So here, let's see, this goes back down to about 2 here. And if I was to change it to 1, yeah, it goes down a lot faster because now the second reaction has a much higher K value. So yeah. I've imported things, and the way the interface works is that these are, well, here, let's print the SBML. Nope, never mind. That's just going to be confusing. The way the interface works is that these are basically in SBML, they are called ports, but here they just are sort of obviously arguments to your different, to the different submodels. So we're pulling in this one reaction submodel, and we're giving it these arguments just like it had up here. And we don't have to use values. We could actually like set this 0.6, 0.3 like this. It would look the same. But I've sort of set these things automatically. I think, let's see what happens if I do this live. All right, hey. So now I actually gave it, so there is no, so I set S1 to 5, but I didn't need to because there is nothing called S1 anymore that actually is a function of a reaction. So it made sort of this temporary variable underscore ant1 that is that first reaction, and just gave it a value of 5 and then proceeded from there. If you wanted to do something more like, who was it? Was it Will? You were the one who wanted to sort of import 2 different models, right?
Yeah.
So let's see here. Yeah. Based. So if you had, I'm not going to make something that's actually here, but correct here, but say like, what I call this. And by default, it won't come with anything. And then you have another model, I don't know, citric acid, or what's a good add-on to glycolysis? Add-on.
Acetyl-CoA.
Acetyl-CoA, sure. CoA, it has stuff also. And let's say they both have glucose in them. Glucose equals 5, right? And then we have, but this one has glucose, but it calls it something else, right? So, sure. We'll say model 1 is just glycolysis, and M2 is acetyl-CoA, and we'll delete the rest of it. Let's see, what else do we have to do here? Let's say K equals 5, and that, and X equals 3. Right. All right. So in this case, the only thing that happened. Oh, here, let's say that X is glucose. So we're going to change this. K times glucose. Okay. Got it. All right. So now we have one submodel. We have 2 submodels. the second one doesn't do anything right now. We basically only have our first thing. And you'll notice that the name it gave it was M1 underscore glucose and M1 underscore Y, because it basically gives everything its own namespace. But what you can do is you can say M1.glucose is M2.glu. And now it starts from 3 instead of from 5, because basically, so this line tells you that it's the same, that those two things are the same thing. So we no longer have as many variables in the model, and glucose was set to be 5 in the glycolysis model, but it was set to be 3 in this model. So once we've combined them and given it a priority, you can sort of read is as is now. M1 to glucose is now M2.glu. So M2.glu takes priority, and it starts at 3 instead of 5. If you had, let's say, G-deg, glucose, nothing at a rate of K degradation times glucose, K degradation equals 0.2. Okay. And we have, and we'll give the same thing here also. So degradation at K degradation times blue, K degradation equals 0.2 here. No, that's not helpful. Oh, sure. Yeah. Does that do everything the way it should? All right. So now glucose is degrading a little faster than it should. So if we, let's see here. So this, see, it looks like that for that. If we were to comment this out, rerun it, you'll see it's not as steep. So what's happening is that both submodels are degrading glucose at some rate. So if you now say, but you can combine these just the same way as you did the other one. So deg is M2 glu deg. And now we only have one degradation rate. And if we get the current SBML and look at it sort of under the hood. Oh, in fact, here, let's not do this. Let's do. Ah, look at that. Okay. So under the hood, once Roadrunner gets to it, it doesn't know anything about hierarchy. So it flattens everything and proceeds. So the combined reactions here look like this. So it says, here is your two reactions. And you'll notice this first one, it got from glycolysis. And the second one, it got from acetyl-CoA. So here, let me do a reset first, because then you can see the original numbers. What you were seeing earlier is the actual antimony version of it as it was after it finished its simulation. So in this version, we have since we reset it before asking for the antimony, it has that at the beginning of the simulation, glucose was 3, which was a value that it picked up from acetyl-CoA and not from glycolysis, etc. And then those are we still have this M1 K degradation as well as the M2 K degradation, but the M1 K degradation is never actually used in any remaining example. So if we wanted to get rid of it, let's do that. K deg. We can actually say delete M1.K deg. And that's just sort of it doesn't like it. All right. Well, I'm not sure exactly what's going on there, but there. Anyway, you can use delete to get rid of things. It may take a little bit of trickiness to do that correctly, but we're at 4 o'clock. I don't think I have anything in particular. Oh, I wanted to show you how to import a model from biomodels, and we don't really have time for that. But let me just show you that real. I will just show you the basic thing. Right. Oops. Copy, paste. There we go. If you can load something in from a URL, here's the URL for this. And then you can reset. Actually, you can just do Antimony and it'll get, you don't have to reset it for that, I think. So it plots it and then it shows you the whole thing. And there's all sorts of stuff going on, and we're a little out of time. But if you are interested in what a large model looks like in Antimony, it's going to look something like this. This is a particularly large model. There's all sorts of things going on. There's a lot of assignment rules here. So these are things that are just all these liver, kidney, plasma are all set to very specific values all the time, which presumably change in time. There's all your reactions. There's an event. Oh, we have T0 equals false, which means that if, well, that's not really necessary, but anyway. Oh, yeah, okay, anyway. And there's all your species initializations, compartment initializations. You'll notice there's a lot of things have units, which are also possible to do in SBML and Antimony, although it gets a little bit complicated with times. But if you are interested in learning more, the easiest way to sort of find out interesting features of Antimony is to import a complicated SBML model that has it in it and look at it and see what it looks like. So there we go. Are there any other questions?
How do you deal? I was looking at some mitochondrial models in SPML, and I'm interested in mitochondrial potential.
Mm-hmm.
How is that handled here? Is that
electric potentials?
Like electric potentials?
Yes.
Yeah, like I think it is often handled with a quote unquote species as your potential.
Okay.
And then it's a number like anything else. SBML calls things particular, it calls things reaction, it calls things species, but in reality a reaction is just a process, and a species is more just sort of a model variable. It is a thing that changes with time, that can be changed by the processes in the model. So you can say that the species is the electric potential.
Do you have to do anything to account for the fact that when you model this, you have volume is already factored in? So I guess you just you would have to set the volume
you could
equal or something. Yeah. Okay.
You could if you leave the volume at 1 and don't change it, then that will work. The other thing you can do is that you can say you can say a particular species has only substance units. That's something that's a flag in SBML, and I think you can do it. You can do it. I think it's called substance only. So you can say substance only species S1, and now every time that value shows up anywhere, it will always be its amount and not its concentration. So basically, it never has to calculate its concentration because it always uses this as amount.
By the way, your electrochemical question, presumably these are voltages, right?
Yes.
So, and you've got a rate of change of voltage. It might be easier to put those in as directly as differential equations into the
just say like the rate law basically is.
Yeah, the rate law.
Yeah.
Okay.
Yeah.
I'll have to look at how they are set up in the models I was looking at.
Yeah, have a look. They're probably differential equations, and you can just write those out as you find them.
Yeah.
Okay.
Yeah.
All right.
Okay. That's it. Thanks very much.
Yeah. I'm happy to. Here, I'll put my email in the chat. If you have questions afterwards, I'm happy to chat. I am lpsmith@uw.edu.
Thanks. That was wonderful. Also, I tried to download the Python file, and I think we have to get requests or get access.
Oh, did I not give? Okay.
Really appreciate it. This was wonderful. Very
Yeah.
helpful for what I'm doing.
Good. All right, I will try to share things. Oh yeah, look at that. Anyone with a link. I thought I had done that with a directory, but apparently not.
Is it shared now?
Yeah, let me share everything.
What are you running on, Will? Mac, Windows, or Linux?
Windows.
Okay. That's the least problematic one.
Oh, good.
Yeah.
It tends to
the
be our
Mac
default
users are a bit
development
fiddly.
environment. So,
Yeah.
all right, I just changed everything to be shared. So hopefully you should be able to download it now. I will stop the recording.
Okay,
Goodbye,
thanks,
everyone on
Rob.
the recording.
Yeah, bye now.